Good morning, everybody. I'm John Maxwell, W0VG, and I'm one of your presenters this morning for IP networking and routing with Willem Schroeder, who's sitting down here to my left. You can see his arm. Bear with us. We lost our director, and last minute, Mark Skelton decided to step in and help us out. Rob Wright got COVID, so he's benched until further notice. So without further ado, I'm going to turn the morning's events over to our crack team. But Rocky Mountain Ham Radio, remember, is a 501c3. Your donations are always welcomed and appreciated. We have a big network that we're trying to take care of. What we do here now for RMHAM University in the online arena is significantly larger than most people would expect, and I can show you what it took us to do this. If you want to turn my camera on here, I'll fire this up and I can certainly show you what it takes to do this. All right, so what we've got going here is we've got a camera on a tripod here, which allows us to show whatever's going on in the back here. We've got lots of audio equipment here. We've got Mark over here in mission control, and he's got essentially 2 computers and audio equipment running here with a full 16-channel mixer. Up here on the tripod, we've got a steerable camera. We've got a nice little Nikon D800 here, which we can't seem to get working this morning for the close-up shots. And then for Steve Surley, the back of the router and audio mixing console is right here. And we've got Dean sitting in over here because he's going to do our presentation for next month. So he wants to see how this works. And that's all we have in the room. But there's lots of moving parts to try to be able to do this. So if Willem wants to take over and go ahead.
So can we switch to the screen? So good morning, everybody, and welcome to another exciting edition of RMHAM University. What we're going to talk about today here is IP networking and routing. So specifically, what I'm going to concentrate on is IPv4, or version 4 of the Internet Protocol. Basically, this has been around since the 1980s, and it was a real paradigm shift to what became before, right? So before, what we used to have was essentially switch circuit networks. So you'll probably remember on Christmas Day trying to call grandma and getting the thing that says all circuits are busy now. So what that was about is that we were simply running out of what used to be copper wires, but later at least got a little bit more sophisticated with multiplex systems. But you had a circuit that goes from A to B, and that's how you actually made a connection. What IP introduced is the concept of a packet switched network. And essentially what that does is when you start at one point and you want to go to another, you have all of these various wires that contains packets. And the packets are basically the long message that are chopped up into discrete chunks and then can share that same wire to transfer the information from A to B. And the key advantage of this IP switch network is, first of all, that it's decentralized. So in order to get from A to B, all A needs to know is where to send stuff to next. It doesn't need to understand the entire path from start to finish. And that gives us the ability to build a network that is both robust and has all of these failover characteristics. So The other wonderful thing that was introduced by IPv4 was that it has 4 billion unique addresses. And of course, we thought that we would never run out of addresses because, you know, you would have like 100 computers worldwide. Well, that didn't quite turn out the way that it was, but IPv4 has been incredibly robust and has survived way longer than people expected. There are some things that are coming after IPv4, but for what we're going to do here today, all I'm going to do is concentrate on is IPv4 per se. And essentially what the internet consists of is a network of networks, right? So what we're actually going to be doing is figure out how do you actually address things on a particular network. And then if you're trying to address somebody outside that network, how does that actually happen? And we typically refer to that as routing. So what I wanted to show you here is just something absolutely miraculous. So my computer right here is connected by this blue wire that runs all the way around and then connects to this router up here on the NetLab. And I'll explain the NetLab in a little bit. But basically what I'm connected to is right here. And what I want to do is talk to this device right there that's plugged into this router over here. So what I'm going to do, if you can switch to my screen again, is basically say SSH to, that's not very clear.
It can't get any clearer.
Okay. And basically what I've done is I did this connection with the -V option so that it actually goes and does a whole bunch of negotiation that you can see it's doing here. But it's basically establishing a session where I use my screen and keyboard. Then while all of these magic wires, it connects to this device here and then goes through all of this maze over to this device over here. What I particularly wanted to point out, though, is that I am now going to introduce a failure to the network. So I have unplugged this piece of wire. And it turns out that this piece of wire was one of the critical components. I was actually connecting via this wire between these two devices. However, if you look at my screen, it still works. And what it now needs to do is to actually take a very circuitous path to get there. It turns out that this network healed itself. And what it essentially did was to see, well, the path between Saddleback and Thorndon, which is the route that I normally would have taken, is now broken. But I can discover that there is another path, which is I can go down here to El Magre and then follow this red wire up here to Thorndon and then get there. So that's one of the key advantages of using an IP-based network in order to connect, for example, your repeaters together or whatever else you need to transfer data between. That there are technologies built into IPv4 that allows us to overcome system failures and to also find optimal ways of connecting between the two devices. Some people would call this magic. We call it engineering. So how did IPv4 come about? Come on, give me the screen. So let me first describe the RMHAM NetLab here. So what we've got here on the NetLab is a simulation of what our actual network is. So the purple wires that you see everywhere here are actually microwave connections in the real world. And what it actually consists of is devices that look kind of like this, right? It's a fairly large 2-foot typically microwave dome with a radio on the back. And what that allows us to do is to make microwave shots between all of these mountaintop sites. Well, on the NetLab, those are simply represented by a little purple wire that runs from one device to the next. But basically what this represents is probably about a quarter of all of the devices that we have on the network. There's 32 devices in this particular setup. In reality, we've got about 120 sites in our network that are all connected by microwave. The wires that are red are represent VPN links. So in this case, for example, at Almagre and at Thoroton, we actually also have commercial internet access. And so what we do is set up these VPN tunnels that allows us to ride commercial internet in case of some kind of a failure, or if we need to back end into the device because one of the other microwave links are down. We don't primarily rely on those, but we do have that as a backup in case we need it. And we have a very good relationship with the ISPs to actually help us put all of this together. There are a few blue wires on here. So for example, this one right here, and the one that runs from this device to that device, those blue wires represent local connections. So those devices would actually be on the same, at the same site. The little Raspberry Pis that we have up here actually represents devices that are at Thoroton. So at Thoroton, we have a server that runs DNS and NTP. And so this is what we use to synchronize the time between all of the devices on the network and also do the domain name resolution. The device over here that reads commercial internet actually represents all of the internet. It's basically where all of these red wires connect to, and then through some clever routing, we basically make this device pretend that it is all of the internet, and then of course reconnect to devices such as Thoroton. Also connected to this device is this box here that's called Hacker. We basically use that for penetration testing, so we can try to break into the network using that and make sure that our firewall rules and all of those kinds of things work correctly. So the long and the short of it is that what this board represents is how our network actually works. It is automatically routed using OSPF, which is the technology that we use to route our network. And so it deals with failovers and all of those kinds of things. But primarily what we use the board for is training. So the people in our networks operations group can break things here, and that's okay. But we also, of course, use it for testing. So for example, one of the things that we're testing right now is to switch over to router OS 7, which has some very interesting challenges. So still trying to get it to work. The last thing I'd like to point out is over here, we actually have some network monitoring going on. So this monitor is connected to our DNS NTP device. And what it simply does is to check connectivity to the rest of the system. So as long as things are blue, everything is fine. If I fail the link again, you'll see that for a while, there'll be some packets lost, and then it essentially recovers once it finds the new route. And so what that allows us to do is make sure that the NetLab keeps working while I'm talking to you here, so I don't get embarrassed because the system doesn't do what I want it to do. So the other thing that's interesting of this is what we're using for the entire network is hardware that's made by MikroTik. So the advantage of using the MikroTiks are that they give you the capabilities that you get from gear such as from Cisco, except that the cost is probably a tenth or less than what you can get from Cisco. It runs basically a custom Linux kernel that you can use for routing. It supports pretty much every routing protocol that you could ever need. IPv4, of course, is sort of the backbone of everything that we do, but it supports OSPF and BGP and all of those kinds of things. But the big difference between this device and the ones that you can get from the Best Buy is that any port can do any function. So this device right here is our workhorse at all of our mountaintop sites. It's a router board 2011. It has 10 ports on it. Whoops, sorry. It has 10 ports on it. And we can basically make any port do any function. And so because there are 10 ports on it, it's typically what we use at most of our internet sites. If we need more ports, this is a CRS 2013. Basically just has 24 ports rather than, or actually if you count the SFP cage, 25 ports. And then I don't have one to show, but for the really heavy duty sites like Thoroden, we use the Cloud Core routers, which look exactly the same, but cost 3 times as much and actually have much stronger processors. What I'm going to be talking about today essentially uses this little device here. This is an RB750, and it is a 5-port device that we will use as, whoops.
Uh-oh, we just lost our hacker.
Oh, that's okay, I don't need it. This is basically the device that we will use for most of our demos today. It's basically got 5 ports. And the way that I'm going to configure this is that I'm going to use the blue port as the connection to the rest of the network and use the orange ports as the local connections. But that doesn't have to be. The big advantage of these devices is that any port can do any function. The other thing, of course, is that it has a very robust infrastructure. So I'll show you several times the Winbox program. What Winbox allows us to do is have a GUI to actually configure the device, but you can also SSH into the device and actually configure it from the command line, and I'll show you some advantages of that as well. These devices are actually pretty reliable given what they cost. They, like anything else, pretty much don't withstand lightning. So if it does take a direct lightning strike, the device does get blowed up. But then, they're actually moderately inexpensive. These guys go, if you buy them secondhand on eBay, go for about $20, $25. New, they're about $50. If you use one of the larger devices, I think the RB 2011 is about $100.
105-ish.
Dollars each, and then the CRS is about $150. So relatively inexpensive equipment compared to what you would get from Cisco, which would typically cost several $1,000s. The MikroTik hardware is largely geared towards the ISP or the wireless ISP market. So there are also devices such as this guy over here. This is a CRT, or that's what they call this particular device. It's basically a flat panel
QRT.
that has, what did
That's
I say?
QRT. You said CRT.
Oh, geez.
We don't do CRTs anymore.
I actually have some of CRTs in the back. Basically a panel radio. This is good for probably about a dozen miles or so. And then the other little one here is called a Lighthead Grid. This is about a $50 radio. The radio actually is right here in the nose, and it has mostly a plastic housing and then a metal reflector. And this is good for probably about half a dozen miles to connect from one device to another.
And they're really light. So if you have to hike them to the top of a mountain, it's great.
Right. And so the big advantage of the MikroTik hardware is that it is the same operating system, whether you're dealing with one of these routers or one of those radios. And actually, the radio is also capable of doing all of the routing functions. So the big advantage of Router OS is you can literally do anything. The disadvantage of Router OS is also that you can do virtually anything. So it takes a little bit more configuration to actually get going. So in terms of IP, there are a whole series of very classic tools that we use to actually test the system. The common ones that you've probably already encountered are called ping and traceroute. Ping, basically, we use to test end-to-end connectivity. Traceroute is how we test how we get from A to B. ifconfig is basically the Linux command to see what your internet configuration is. On Windows, it's called ipconfig, and then route displays your actual routes. So I just wanted to take a second and actually show you those particular tools because we're going to need them throughout this class. So ping basically allows us to just test connectivity to the far side. So in this case, I'm connecting between my laptop and the device that I just showed you before. And basically what it tells me is that every packet that I sent came back. So we don't have any lost packets in the process. And generally, because all of these connections are via wires, we're doing it in less than a second. The program that we sometimes use in addition to that is called cping. This is basically a program that we developed here at RMHAM. And what it allows us to do is to basically ping a whole bunch of devices all at the same time. So you'll see they're all coming up blue. We're all connected, except for the demo site, which I'm going to add later.
Jeff N2XGL has a question. He says, what is that software running connectivity monitoring? NTOP?
Oh, no, that's cping.
And then there's another one down below that says, that's Willem's custom cping. Not sure if it's been open sourced.
Yes, it's open source. I'll send you the link if you ping me on it.
Great, thank you.
And the other built-in thing here is actually also traceroute. So it'll actually, if you select a particular device, it'll show you to the traceroute to it as well as the history associated with it.
Sorry about the weird resolution, everybody. It's a kind of a weird lash up to be able to get Willem's laptop to the network so that we can actually see what it's doing. We're lucky we got this morning.
And one of the things that's important to us is not just that the packets are getting through, but also the timing. So in this case, what we're actually displaying is the ping times. And of course, because we're all Ethernet connected here, the ping times are all very, very low. But when we run this out on the real network, we want to make sure that our ping times are very consistent because the VoIP system doesn't work very well if the ping times vary too much.
And what is that called? That's called jitter, when the ping times change rapidly.
Right. Now, of course, the other thing, or the tool that we use to basically test this, whoops, sorry. I can't talk and think at the same time. The tool
you were
that
a teacher.
I don't have to think about that stuff. So what traceroute simply does is to check all of the devices that it takes to get there. So this is an important tool to make sure that the network is actually behaving the way you think it ought to be behaving, that you're following the right path from A to B. ifconfig basically tells you about your local connectivity. So in my case here, I've got Ether0, which is basically Ethernet port that I'm plugged into. The loopback, which is basically the 127 address, my wireless LAN, which I currently have turned off, and then a VPN, which basically allows me to connect between the NetLab and myself here internally. Basically, what ifconfig is useful for is just figuring out what exactly is happening on your local machine. And then, of course, route basically is to figure out where packets are being sent. So at this point, the only two devices that are active that I can send packets to is my Ethernet port and then that VPN. So what this basically tells me is what net masks goes where. And we're going to obviously have to figure out how to configure the network to set all of those things correctly, which is basically the whole object of this class. So we talked about IPv4. So what other versions of IP actually existed? IPv4 came about in the early 80s, but before that, there has been development at the various labs with different experimental versions of IP. So IPv1, 2, and 3 are really early development versions of IP. Actually, what most things was actually being changed during that period was they were actually trying to figure out how to make TCP/IP work well. And so IP2 and IP3 were basically just different iterations of TCP/IP until they basically figured out, well, this is not a good idea. We should separate the IP part from all of the things that are on top of it. And so basically with IPv4, the IP definition got separated from all of those others. IPv5 was an experimental quality of service version. It started being used in the late 80s, and it was a way that people like the phone companies could put special routing marks on the packets to deal with things like low latency and top priority in terms of getting the packets back and forth. But it never really caught on because our networking technology grew to the extent that it basically solved the problems by just throwing more wires and better technology at it. Of course, IPv6 is really the next thing in IP networking. So IPv6 expands the address space from 32 bits to 128 bits. And of course, we're all laughing because who's ever going to need 128 bits? But it's only been about 30 years since we thought 4 billion addresses is more than we could ever need. So, watch out for IPv7. It's probably coming. So what do we use IP for? Well, IP is basically the most successful protocol ever. I mean, essentially everything that we call the internet runs on IP, right? It's the most ubiquitous network that exists everywhere. But we also use it for other reasons. So for example, the RMHAM NetLab is just a small fraction of what we actually run out in the real world as the RMHAM network. We use that to connect a whole bunch of different repeaters together, and we use it to manage all of those repeaters remotely. So what IP allows you to do is basically move any kind of traffic from A to B, whether it's commands, whether it's voice over IP, or whatever we want to use. But IP is basically being adopted by everybody else. So my iPhone actually talks IP to the rest of the cell network, right? So the entire phone network has gone to it. The Department of Defense is running all of their long distance networking now on IP, which some people think is not a very good idea. NASA uses a special version of IP for their deep space network, although because you're dealing with really long delays on the order of many minutes to sometimes on the order of hours, depending on how far out you are, it's basically the same technology overall. And of course, the applications that we can use for this is numerous. Most of it we use it for is data. So all of your HTTP requests to load a web page or sending email or transferring files with FTP or anything like that is done over IP. Voice over IP is basically taking over all of the communication systems. The streaming video that you're seeing right now is basically just built on top of IP, and we're basically adding special protocols to actually add things to that. And of course, we have the Internet of Things. So here are examples of a really small chip that actually runs an IP stack, which I can now connect to, for example, a temperature and humidity sensor to actually see, what the temperature and humidity is. Or here is a relay board where I can just send via IP a command to this little device to turn this relay on or off, right? So basically your smart fridge and your smart microwave and your smart toilet are all run over IP, sometimes very inappropriately. So how does IP basically work, right? Everything needs to have an address. So that address is basically the building block that makes everything work together. So the address is a 32-bit number that we typically represent as what's called the dotted decimal notation. So it's basically 4 octets, so 4 numbers that each represent 18 bits. So if you look at a number like 10.30.20.6, which happens to be the address for my little DNS server here, that is basically the binary number that is shown over here. But we break that number into 2 parts, what we call the subnet part, or sometimes called the network part, and the host part. And the convenient way of thinking about it is that there are 24 bits that tells it what network you're on or what subnet you're on. And then there are 8 bits to tell you what device on that network you are, right? So that's total 32 bits is what you need to address the device. But in order to find that device, you need to distinguish between the host part and the network part. If the network part matches my network address, then I can talk to that device directly. So we're on the same subnet, and I can directly talk to that device over there. If, on the other hand, that device is not on my network, I need to figure out, well, how do I get it to that device? And that's basically what routing is all about. So the whole idea behind taking this address and breaking it into a host and a network part is simply how to figure out how do we get this packet to that device. We can also write that using that shorthand 10.30.20.6/24. And what we're basically doing in that description is combining the address and telling it how many of the bits actually becomes part of the network part, which just is a shorthand for writing out the combination of those two, and basically coloring those bits into the different parts. IPv6 works exactly the same way, except that instead of doing just 32 bits, there's 128 bits involved, and there's a few other things. But for purposes of what we're discussing here, the difference is not important. So I used the term subnet a few times. What is a subnet? Well, a subnet essentially is a network that is part of a bigger network. So if you look at the NetLab, what we basically have for every device is its own subnet, and all of the devices that are connected to the local area network on this device can talk to each other without any interaction with the rest of the system. The overall network, though, is basically a collection of these subnets. And what we need to figure out with the routing is that if there is a device that we want to talk to that is not on our subnet, how do we do that, right? So the big distinction here is between the local area network, basically the devices we can talk to directly, versus the rest of the network. So one way of thinking about this is you're on your home network, and you've got your iPad and your desktop computer and your laptop or whatever else. Those devices are all on the same subnet and they can all directly talk to each other. But if you want to talk to Google, do you need to know exactly how to get to Google? Well, no, there is a device called a gateway that knows how to get to Google, and all you need to be able to do is to talk to it, right? But let's say you want to expand your home network. How are you going to do that? Well, you can buy some cheap devices, right? This is an example of a network hub. What this device simply does is anything that it receives over any of these ports, it sends out over all of the other ports, right? So it just rebroadcasts all of that information. If it's a slightly smarter device, which we call a switch as opposed to a hub, it may actually know what is connected to each of these ports and try to not send everything everywhere, but at least sort of direct the traffic a little bit. But the key thing about this is that these devices are not terribly smart. What they're essentially doing is simply sending all of the network traffic to all of the devices, and every device needs to figure out whether this information is directed at them and then or ignore it if it's not.
Can I make another comment about hubs versus switches?
Go ahead.
All right, so a hub is, as Willem says, it's a dumb device. And there's a lot of folks out there that have tried to build networks like we've done, but they've built it as a giant switched or hub network. And if you have a device on that network that goes crazy, all of that traffic gets sent down that network. So if there's a device that's not acting properly, all of the traffic that's bad gets sent to every other device in the network, and it's called a packet flood. That's a bad thing. That's one reason that we don't use bridged networks. They are a bad idea.
And you can just imagine if the whole internet worked like that, then every packet that any other device in the world sends is going to suddenly show up on your doorstep, right? So one of the key components in actually going from a switched network or a bridge network to a routed network is that the traffic is sent to the right place in an intelligent way. So on your each subnet, there are actually some special addresses that are reserved. So we need to have a name to call the network as opposed to devices on the network. So that is done by making the network, the host part all zero. So that's a reserved address. So in the case of Mount Thornton, where we use the 10.30.20 network, 10.30.20.0/24 represents the entire network. There's also the network consisting of all ones, which is called the broadcast address. So if you want to talk to every device on the network all at once, which is not a smart thing to do, but if you needed to, 10.30.20.255, so all ones is the way that you then address everything. So every network is going to have at least 2 reserved addresses. So if you look at a subnet, obviously you only have so many bits to actually address the network or the host in the network, and 2 of those addresses are always reserved. The only exception is the /31 and 32, which I'll talk about later, but for now, don't worry about it. There's also a few special addresses that we typically use in every network, but it is not actually defined as part of the IPv4 definition. So for example, in the RMHAM network, the lowest possible address that's not the network address, we reserve for the gateway. So we always know what the gateway address is going to be. So the .1 is always the gateway. There are other conventions that you can follow, but that is a convention that you have to establish for your own network. Similarly, there may be a DNS address and similar things like that, but that is simply a convention. It's not required. So we referred to this just briefly before, but the big difference between routing and bridging, it has to do with the intelligence of the devices that you're dealing with. I always tell my students that you have to remember that computers are dumber than dirt. Well, actually, they're dumber than a box of rocks, right? And so if you actually look at a device such as this is truly as dumb as a box of rocks. It basically just sends everything everywhere, and it doesn't try to do anything intelligent with the packets. If you go to Best Buy and, for example, buy one of these devices like this Netgear here, it's about as dumb as half a box of rocks, right? Actually, you know, the more rocks you have, the dumber it gets. So a half a box of rocks is not quite as dumb as a full box of rocks. But it basically has a specific way that it actually is going to send that traffic. So if you, for example, use one of these devices, it actually has a switch in it that tries to learn what is on each port and only sends the traffic that is destined for devices on that particular port down each of those ports to actually connect or limit the amount of traffic. The advantage of this is that it, to all intents and purposes, figures out for itself how this works. So I can simply plug in a wire into this port, plug it into that port, plug it into that port, and then plug it into my device. And it will basically figure out what it needs to do because it doesn't do a whole lot of very intelligent things. But the key thing in all of that is that that does not scale, right? Because basically that traffic or each of those devices needs to know about all of the devices that are on that network. What we have in the case of a bridge is something that is like a special case of a switch. So consider, for example, a situation where I have this piece of microwave gear here and another piece of microwave gear here, and they're talking to each other. They are set up as what's called a bridge. A bridge is just a special kind of switch where it knows what's to the Ethernet side of it versus what's over on the microwave side, because typically this microwave side is the side that is going to be the thinnest pipe, the lowest throughput to there. And basically what the bridging does is it just knows what devices do I need to send via RF versus what devices do I talk to over the Ethernet, and it makes a somewhat smart decision about it. However, it needs to know all of the devices on both sides in order for this to work. And so typically that's only done on a particular subnet. So all of those devices are within the same IP space, and the bridging actually happens more at the Ethernet level. So since I've been talking about internet or Ethernet, I guess I should sort of explain what it was. So it turns out that Ethernet and IP sort of got developed at roughly the same time. And you know, in the early days, there were actually a number of other technologies that used Ethernet as well. You may all remember the NetBIOS that Microsoft used to push, right? It is a non-routable protocol that uses Ethernet as the way to connect between two devices, but they actually have to be physically connected and they can only be switched between the different devices. But Ethernet was also one of the main reasons why IP became so ubiquitous, because it is a good way of connecting IP devices together. So it started out at about 10 megabits per second on a piece of coax, right? Ether basically used the old term ether from the 1800s as the way to describe this amorphous structure through which radio waves worked. So what Ethernet simply does is allows you to connect a whole bunch of things together, and it has a way of figuring out how to talk from one device to the other. Ethernet has basically been the most successful way of connecting devices together. Right now, over copper or most likely fiber, the speeds are starting to reach about 1 terabit per second. So tremendous throughput on a device that basically allows you either connect point to point or on a local network. There were a number of other technologies that were developed in the early 80s, such as token ring and FDDI and various other things like that. But basically, Ethernet, just like IP, has turned out to be the most successful of all of those protocols, and it's the one that we're going to be using today. And of course, all of these devices here are really Ethernet devices, right? So you can get Ethernet devices of various smartness. In Ethernet, you also could get to a situation where you've got a loop in the wire. As long as you've got a smart enough Ethernet device, it actually implements a technology called SDP, the spanning tree protocol, to figure out which way around to send packets. Otherwise, you can also get these things called broadcast storms.
Can you explain what a loop in the wire means?
Oh, so if I basically connect this device to that device, and then I use another wire to connect this device and that device, notice that we have a loop, right? So if this device needs to talk to that device, which wire does it use? If it sends a packet from here to here, and this is a dumb device, and it basically sends that packet to everywhere else, it gets sent back to the first one, which then says, oh, this new packet just came in, and it sends it again. So that same packet just gets sent round and round and round and round, and that's what we call a broadcast storm. So if you have a switch, it has a protocol in it to actually resolve those kind of issues, which is called that spanning tree protocol.
It doesn't resolve it, it stops it.
Well, true, that's correct.
Resolve it means you've got to go figure out who plugged the wire in 2 places.
Right. Don't do it.
And it will happen on your home network too. If you had a situation where you had a cable that was plugged into the same router switch port twice, it will take your internet connectivity down, and you think it's Comcast or CenturyLink. Well, no, it's probably you, because when you plugged all that stuff back in, you plugged the same cable in twice.
Well, and the same thing will happen is if I take my laptop and I connect to the switch via Wi-Fi, and then I also plug in the Ethernet cable and plug it into the same cable, right? I've just created a loop. One is over RF, the other one is a connected cable, but I'll still create those same problems. The key thing, though, is that the Ethernet is sort of become almost synonymous with IP, although they're very, very different technologies. So we're getting to the point where we're actually going to be configuring some stuff. So we just need to get some technology straight. So the IP address is a unique 32-bit address for that device. And that IP address is always a 32-bit number. We can color some of those bits differently, but you need all 32 bits in order to address that device. The way that we describe the network as opposed to the device itself, we refer to as the net mask. So it basically is a number of bits that are used to be ANDed to the address. So what an AND simply does is if the bit is a 1, we'll keep the value. If it's a 0, you basically zero it out. So if you take that net mask and you AND it with the actual IP address, you get the network address, right? Because the network address has all zeros as the host value. And we can represent that in a number of different ways. The line here with the 1s and the 0s in different colors is literally what we want to reproduce. We can write that either as /24, which means there's 24 1 bits and then a 0 bits. And there can't be, you can't go 101, right? It has to be basically 1s from the left to where you stop and 0s from there to the right. Or you can also write that in dotted decimal notation as 255.255.255.0, right? That's just the decimal representation of that binary. If you actually want to explain both at the same time, so both the IP address and the net mask, right? So if you're on your laptop computer, for example, and you want to tell it what its address is, you want to tell it its actual address plus the net mask all at once, you can write that, for example, as 10.30.20.6/24, right? So it is both the actual IP address and then what part is the net mask in just a simple way. And then the key thing, of course, is the gateway. So the gateway has to be an address on your local subnet, right? Because you can only talk to devices on your local subnet, including the gateway. However, the gateway is that clever piece of hardware that says, well, I don't know where to go to send this to, but the gateway knows, right? So the gateway is where we're going to send the traffic that we don't know what to deal with. In addition to IP, there's actually something called the domain name system, or DNS. Now, in order for any of this stuff to work, we don't need DNS, right? And if you are John Maxwell, you despise DNS because it's just for people, right? But it's basically just a symbolic name to call things, right? So you want to be able to say, go to www.google.com, right? You don't want to know what the IP address of Google is. Or if you want to go to Yahoo or something else, it's a way of giving something a symbolic name that a person can remember, right? So what DNS simply does is it gives you a translation between human readable names and IP addresses.
It's the phone book for IP addresses.
That's a great way of thinking of it. And so when you typically configure your IP device, you typically tell it how to do DNS, right? Because most of us are actually going to be using DNS. But DNS actually works by using IP itself. And so, for example, if we look at a couple of addresses here, 10.30.20.1 in DNS translates to router.thornton.rmham, right? It's our gateway, so we call it router. And then the device that I was talking to previous is called radius. So 10.30.20.6 is radius.thornton.rmham. If you actually look at the color coding here, you'll see that the domain name system works kind of like IP in terms of its hierarchy, but it does it right to left instead of left to right. So typically in our IP scheme, we have the network followed by the host. In DNS, we start with the host, and then we add the network part to it. And the network part is actually hierarchical. So router.thornton.rmham happens to be 10.30.20, but there can be additional layers. So the key thing about DNS is that in order for DNS to work, you have to give it the IP address of a DNS server, right? You can't give it the name of a DNS server because it needs DNS to work before it can make DNS work, right? So you have to actually give it an IP address. And one of the common ones is 8.8.8.8, which is basically Google's DNS, or 8.8.4.4. There's also 1.1.1.1 and was it 4.4.4.4?
7.7.7.7.7.
Right.
Yeah,
So
there's a lot of
it's
them.
easy to remember IP addresses for people like Google to actually provide DNS for us, or in our case, we actually provide our own DNS. So how DNS actually works is it sends an UDP packet to a DNS server. Now, I'll describe DNS in a little bit more detail later, but let's say, for example, we want to know, how do I get to www.rmham.org? In your computer, there is actually a table of root servers. And what it does is it sends a single IP packet to that root server and says, I need to know the address of www.rmham.org. What that root server will reply is to say, I don't know, but go ask 192.19.56.1, which is the .org root server. You then send, so we've sent that packet to the DNS server. The DNS server actually asks the root server what that address is. And if it says, well, I don't know, go ask the .org server, it sends another packet to that .org server and says, can you tell me where www.rmham.org is? It will probably say, no, I don't know either, but RMHAM uses Bluehost as their hosting service. Go ask the name server on Bluehost what the IP address is. It then sends a packet to that server and say, can you tell me what the rmham.org address is? And it will say, yes, it's 23.237.17.75. The server then remembers that result for future reference.
For a while.
And then for a day or so, typically, and then sends it back the answer and says, www.rmham.org is that 23.237.17.75. The key thing is that what DNS simply does is it figures out the IP address.
So,
and from there on, everything works on IP addresses.
if you type that IP address into your browser, guess what's going to come up? rmham.org.
Yes.
As a matter of fact, you don't have to type in www.rmham.org.
Right. So that's a long way to get to the point, which is how we now go about to actually set up an IP address. So what we need to know is our subnet address and the net mask, right? So we need to know what is our local subnet. So let's assume that it's 10.30.20, which is Thoridan. 10.30.20.0/24 is the subnet for Thoridan. And I can use any address on that space except for 0 and 255. So let's say I want to be .6, which is a DNS device. What I need to do is to pick any address within that address space and then assign it as the IP address for my device. The key thing is that that has to be unique, because if you have two devices with the same IP address, whenever you send a packet, two people are going to respond and just really bad things are going to happen. And I won't admit to ever having done that. The other thing that you need to know is what your gateway address is, right? And your gateway address is not determined by the IPv4 standard. It's determined.
Okay, we're about 1 minute out. The video should be much more solid. We figured out the magic incantation. If you guys are trying to capture video for Zoom, if you right-click the source in the way we're doing it, we're using an open broadcaster. If you right-click the screen and tell it, choose the output and send it to one of your monitors, and then capture that monitor with Zoom, it's full resolution, and it's much, much, much nicer. Oh, we can actually see Willem. He doesn't look like fuzzy.
Isn't that actually an improvement?
That is a much more, well, Kathy would think so.
We got a lot of jitter though.
Jitter. Oh, no, what you're seeing is not full frame video, probably. What are you seeing, Emmett?
There's just a delay and in moving and everything.
Yeah, remember it's not 30 frames per second video on Zoom. It's kind of what you get.
It might be that Willem hasn't had coffee.
Well, he has had coffee.
It is not for lack of caffeine. Is the audio still good though, Doug?
You got to turn Willem's mic on. I think his mic is off.
They're hearing you through me. Yes, he did.
Sorry.
He had his mic turned off. He needed to make a restroom break.
Well, the main thing is that I don't think I'm going to show anything that's very animated as long as the video is okay. I mean, the audio is okay.
That's very good quality audio, Willem, the same as we had the other day when we tested. And Emmett is right. We're seeing like 15 frame per second rather, or 5 frame instead of 30. We're just seeing bits and pieces, but it's not a problem. I
Okay,
would continue with your presentations.
great.
Okay.
So let's launch into protocols. So what are protocols? I've used the term loosely a few times, but it's basically agreement on how do we talk to each other. So if I were to say to John Maxwell, "Hi, can you for me I copy coffee not my to bring?"
What?
He's going to say, "What? You just spoke a language to me that I don't understand," right?
German and English. That's the choices.
Right. So even though we are using a common technology to transfer that information, right? My voice box is making sounds, which his ears picks us up and translates back into signals in his brain. It's getting across, but we're talking to different languages. So what protocol simply boils down to is an agreed upon structure to the information that we send to each other so that we can have a common language that we talk to. And these protocols are actually stacked on top of each other. So we'll talk in a little bit of detail about each of these later, but basically at the LAN level, we, for example, have a protocol called ARP, which is how it figures out to translate between MAC addresses and IP addresses. We have a protocol like ICMP, which at the IP level is a way of exchanging routing information, and particularly routing error information, right? Can I reach here or can I not reach there? On top of that, we stack something like TCP/IP. TCP/IP is basically a virtual circuit. It is a connection that I make between one device and another device as a pipe where I can push some bytes down and get some bytes back. And then on top of that, we have something like HTTP, which is a way of asking a web browser, this is the information that I want. Can you send me back the answer to the request that I've made? So the general way that we think about this is called the OSI network model. So it's basically a stack with 7 layers defined, where each layer defines something different. So down here at the bottom, we have the physical layer, right? It's basically the electrical signals that get sent from between different devices. On top of that, we have the framing, which basically is how those pulses are grouped together into chunks of information. And on top of that, we have something like packets, right? So for example, if I'm sending things over an Ethernet port, I'm actually sending discrete packets of information that are addressed to the appropriate MAC address. Those are what's called the media layers. On top of that, we have all of the different host layers. So there we basically have things like TCP/IP, which is a way of establishing an end-to-end connection. And then on top of that, we have, which is called the transport layer. And on top of that, we have, for example, things like the application layer, which is like the HTTP exchange of information, right? So how do I ask for this particular web page that I want to look at, and how is it going to be sent back to me? And so basically this combination of stacked layers is how this all works, which is why I said at the beginning, this is really close to magic. In order for us to do something as simple as pull up a web page, all of the stuff needs to work perfectly. So at the bottom, or basically at the interface between the media layers and the application layers is the IP packet, right? The IP packet is basically how all of this is put together. And basically what that packet contains is just enough information to get that packet sent from one location to the next. So up here in the top, the first 4 bits says what version it is. So that's a 4-bit number. So this will work all the way up to IP version 15. Right now, it just reads 4 because that's basically what we talk about. The next 4 bits is how long the header is, which is basically 20 bytes. In IPv4, it's always bytes, 20 bytes. The type of service we don't really use, but you can actually there ask for whether you're trying to route this with a minimum delay or with maximum throughput or whatever you want to set. Then we have here an address, which is basically the total length of the packet that we're going to send. There's a few other things in here that's not important. For example, if we're trying to send packets that are too big to fit in an IP frame, we can actually fragment that frame and break it up into different parts. And these flags and the fragment offset here allows you to put them all back together in the end. There's a checksum, there's a time to live and stuff like that. The important thing here is the protocol. So what protocol are we talking? Is this a TCP packet? Is this a UDP packet? What kind of packet it is? But the most important things in here are these 2 numbers here, the source IP address and the destination IP address, right? It's basically that 32-bit address that tells it where it's going. And then, of course, it needs to send a reply back. So we need to tell it where it's coming from, which is basically the source address. And then the rest of the packet is basically just the data. And they're basically just tagged right on to the bottom of this IP packet. So the simplest one of those is called the ICMP, or the Internet Control Message Protocol. So it basically consists of just that IP header and a little bit of information that comes right after it. And ICMP is a good way of testing the system, because in the lower part of the operating system, where the network stack is what we call all of these protocols riding on top of each other is implemented, that's where ICMP responses happen. So it's a response that happens very deep into the operating system itself. Actually, it happens right in the middle of the kernel. And what we get from this as a reply to an ICMP inquiry is typically something like this address is unreachable, or you have exceeded the time to live on this packet, or there's a better way to get to this particular address, which is called a redirect. And this protocol is basically what ping and traceroute uses to just make sure that we can talk end to end. And so this is basically what an ICMP packet looks like. So you can see the first part here is just a regular IP header, and then there's a little bit of information added to the bottom. So the type of message is this an echo reply, which is just tell me that you're alive, or is it an actual reply that says this was unreachable, or whatever the status was. And then there's a little bit of other payload data that you can add. So for example, how ping times are estimated is you timestamp the packet that goes out, and then as part of the payload coming back, it sends you the time that you sent it when you sent the echo request in the first place. And then you can just take the difference between your local time and the time that was sent to actually figure out how long that packet took to make the round trip. So ICMP is basically just for diagnosis. Most of the traffic that we actually pass is going to be either UDP or TCP. So what UDP does is it basically sends the IP header and then a payload that is actually useful information. And that works well if the entire payload of what you're sending will fit in one particular packet. So this is good for things like DNS, right? Where you're basically sending it a short character string that says, tell me what the IP address is. And what comes back is basically a 32-bit number that says, this is the IP address, right? So for things like that, UDP is a very good way of sending that information. NTP, Network Time Protocol, is a similar useful protocol to do that for, but there are other more sophisticated things like NFS that also use that. Also, some of the software-defined routing or software-defined networking often uses UDP. So, for example, there are technologies where you have applications that want to talk to each other using their own secret protocol, which they, as a marketing ploy, basically call software-defined networking. Well, it's not really all that software-defined. It's just, you know, a different protocol, but that usually arrives on top of something like UDP packet to actually talk back and forth. So, you know, it basically the intelligence on making something more complete off of all of these small packets then lives in your application, unless it's something like DNS where, you know, the entire answer can be captured. The other important use of UDP packets is for repeater linking, right? So in repeater linking, as well as other VoIP applications, basically you send a snippet of audio, and if that snippet of audio doesn't arrive in time, then you don't really care, right? You're basically going to just drop that particular syllable. And so the whole principle of UDP is that it's a best effort delivery, and it's not necessarily going to make it through, although on a reliable network, it's most likely going to show up. The key thing is that the packets will not necessarily arrive in the same order as they are sent. So because you can have different paths that a packet takes from start to end, or just, you know, other delays in the system, these are all store and forward systems. And so in the process, some of those packets may actually arrive out of order. So it's important that your protocol takes care of ordering those packets if it matters in what order they arrive. So basically a UDP packet looks kind of similar to an ICMP packet, except it adds a couple of things. It adds a source port and a destination port. I'll talk about ports in a minute, but it's basically if you can talk to a particular computer, you may actually want to talk to a different program on that computer, and that's called a port. So basically what the port allows you to do is to do addressing of particular programs on the same IP address, and that's how you distinguish those. And then there's a length and a checksum just to make sure that it arrives intact, and then the rest of it is basically the data, the payload, which is typically, you know, somewhere between 1 and 64 or 64K bytes of information. Of course, the protocol that we actually use most of the time is TCP, or TCP/IP is its full name. TCP is basically the most convenient for us to use for most applications, because what it basically does is it sets up a bidirectional virtual circuit. When I showed you at the beginning how I actually made an SSH connection between my laptop and the router device, basically what it did was to establish a TCP virtual circuit where everything I push down that pipe gets sent and arrives in order at the program at the other end, and all of the traffic that comes back is similarly ordered, and it does all of the error correction. So at the IP level, packets could be dropped. There could be problems with congestion and that it gets rerouted. They can arrive out of order and things like that. So the TCP protocol actually does all of those corrections for you much lower in the operating system. So if you're actually writing an application, in your application, it looks like just an actual circuit between A and B, and things show up at the other end just as you push them in this side, and it's reliable. So every packet is guaranteed to arrive. And so we use this for a lot of things like SSH or Telnet or other protocols where we actually talk from one device to the other. But it's also used in most data transfer protocols, because you want to make sure that if you load a web page, that the entire web page arrives in complete, right? So things like HTTP, FTP, SCP, rsync, all of the data transfer protocols typically establishes a TCP connection from end to end, and then just say, send me this, and the reply comes back, here's what you just asked for. How this actually works is actually pretty complicated. And there's lots of individual packets that are being sent back and forth, but I'm not going to go into the details of that because it's a little bit out of scope. One of the other protocols that we'll actually use here in just a minute is the Dynamic Host Configuration Protocol, or DHCP. DHCP is a convenient way of centrally administering IP addresses for your subnet. So you have a server, a DHCP server, that basically has a pool of IP addresses that it can give out. And your computer sends a broadcast packet to that discovery server that says, I need an IP address. And then the server, and that's a broadcast packet that's sent. It basically sends to all devices on the network. And then the server sees that packet comes in. It says, oh, that's what I do. And it sends back an offer to the client that says, okay, I offer that you can be 10.30.20.6. The client then sends back a packet that says, okay, I accept that request. And then the server sends back another packet that actually acknowledges that, okay, you are now that .6, and I won't give that address out to anybody else. So in that packet, it could also send other configuration information in addition to the IP address. It will typically set the net mask. It will also tell the server what the gateway is. And if you've configured it properly, it will also tell that particular device what the DNS server is going to be. So DHCP is just one of those protocols that actually work at the Ethernet level to actually help you configure your IP address for your device. So let's get to some actual real life demos. So what I'm going to use is this router board that I call demo. So how I configured it is that these ports are color coded, not because they have a particular function, but because of how power over Ethernet works. So this is where you normally feed power over Ethernet in, And all of these Ethernet ports will actually receive power so that you can actually power the device over the Ethernet cable.
And this is a special router. This isn't on a normal home router.
Typically, no, right. And so, but I'm going to use the color coding here to help me remember how I actually configured these ports. So I'm going to make the blue port the port that I connect to the rest of the network with, while the yellow ports are going to be my local area network, which is basically going to be where I have my subnet configured.
It doesn't really matter what goes where, but you're just doing it for ease of layout.
The color codes helps me remember what I did. So the device is going to be called 10.30.80. And because of my convention, the router itself is going to be called .1. Ethernet ports 2 through 5 is going to be the LAN. And then Ether 1 is going to be my gateway port, which is also sometimes referred to as the WAN port, the wide area network port. And I've already configured this to that subnet. So it's the 10.30.80.0/24 subnet. And I have it configured to run DHCP on these ports so that I can actually, if I were to plug my laptop into here, get a DHCP table.
When you say WAN, what's another word for that? Internet.
Right. So this orange wire I am going to use to connect this device to where I used to be connected with my laptop directly. And I'm going to instead plug my laptop here into the LAN so that I am now going to become part of the local network on this particular device. And then the orange wire is going to be how I'm going to connect, if I can find the hole, to the rest of the world. So what will now happen is that I can talk over this Ethernet port to this device, but only if I configure this device correctly. If you were to use one of these consumer grade devices, it's typically set up to do this automatically. But I'm going to have to go and manually do the reconfiguration to actually make that work on this particular device.
How do you know you have it configured correctly?
I haven't, so it's not going to work yet. I will show you how to test that. So basically, if you show my screen, right now, what I'm going to have is that 10.30.80.0/24 is going to be mapped to the bridge. Another name for the bridge is just my local area network or my LAN. Everything else, I'm still going to have to actually set. So, come on, why is my computer locked up?
It's because it's not Windows.
Oh, yeah.
We didn't get any comments from the guys out on Zoom over that one.
What happened to my, why did that go over there? Start it again. So the program I'm going to launch here is called Winbox, and it's basically the program that we use to configure these devices. So in order for me to connect to that network, what I need to do is I need to go and say, I need to set up a DHCP client that I want to connect to the rest of the network. So in this case, I'm going to click add. It defaults to Ether 1 WAN, but I could basically have made it any of these ports, but I'm going to obviously use the WAN port because that's what I physically connected to. I ask it to get DNS, NTP, and the default route from that particular port. And as you see, I just connected me and it said, I got address 10.30.31.199/24. It's going to expire after a while, but of course renew itself. And now my network is just going to magically work. To actually make sure that that in fact is the case, I will do tools ping and say 10.30.20.1. I want to ping. Voila, it's working. Everything is great. So now what I'll do is I'll go in my laptop and say, what address did I get from that? So it gave me the 10.30.80.250 address. Everything is wonderful. If I look at route, it says, okay, my route directs everything to 10.30.80.1. Everything is wonderful. And I can ping 10.30.80.1. That works. And I can ping 10.30.20.1. That's Thoroden. Oh dear, something is not working. Why am I not able to ping 10.30.20.1?
Because you didn't do it right.
So let's think this through. I'm going to send a packet, and I'm going to address that to, well, I rewrote 10.30.20.6. You're going to look that way, right? And I'm going to say I am coming from my local address, which, again, I cheated. I put the wrong address there, but it comes from 10.30.8.6. Let's pretend this was 10.30.8.6. How is this packet going to get to Thoroden? It's going to go from my laptop down this blue wire, get to this device, and says, okay, I want this to go to 10.30.20.6. Okay, this device is a gateway. It knows how to get to 10.30.20.6.
No, it doesn't. It knows how to get to the next hop.
True, right?
Routers only ever know where their next hop is. They never know how to get to the end point, but they know how to get to the next hop.
Right. But this device in particular was told that the way that you get to the next hop is to send it to here. So it's going to go down the orange wire, and it goes to the AC0KQ router. Now, if you look at this, it has only one wire coming out of it. So what it says is, okay, well, I know how to get that to Thoroden by simply sending it to the next device that I sent stuff to, which is the Saddleback router. Now, here's where things get complicated, because as you can tell, I came in on this particular purple wire here, but I can go out on any of those purple wires. How does this device know where to go next? Well, that's where the routing magic comes in that I will explain later. But it basically is going to say, well, I actually know that Thoroden is just right over here because 10.30.20 is directly connected to via this wire. So it's going to send it there. And then finally, it's going to send it to the DNS server, which is 10.30.20.6, which is where I sent it in the first place. Nobody so far ever cared about where it came from. All they looked at is the to address to figure out where it gets sent to. And this looks up and it says, okay, I now need to send back a ply of 10.30.80.6. Never heard of it. Don't know where to send a reply to. Wait a second. How did it not know? This guy made a DHCP client request to this guy over here, and it got an address. But what address did it get? Well, let's look. I can go to IP addresses, and it tells me it gave me an address of 10.30.31.199. So the network knows how to get to 10.30.31.199, but it doesn't know how to get to 10.30.80, because 10.30.80 is my private network, right? So the reason why we use these 10 dot addresses for our network is that there are special subnets that are reserved for reuse of IP addresses, right? They're called private subnets. And there are several of these, and 10 dot is one of them. So the reason why we use 10 dot is that we can, in our internal system, use these addresses without confusing the rest of the internet that these addresses are being used somewhere else. So does that mean that your laptop at home needs to have a special address that it can talk to Google to? Yes, it does. But your laptop doesn't have to have it. Your router has. And the way that we fix that problem is using network address translation. And what we do is, in this case, is to go to IP firewall and say, I want to do native address translation.
Network address translation.
Sorry, network address
NAT.
translation.
You'll hear that in home routers a lot, because home routers generally use NAT all the time.
So what I want to do is I want to do what's called source NAT on that Ether1 WAN address. And the action I want to do is to masquerade.
On the cheapy routers, you don't have the option to really change that. It's just set up to do that. No, those routers are not assuming that they're being put into a commercial network of any kind.
Right. And so now notice that my routing now works. And if what you're using is this guy, that is your only option, right? Native network address translation is the only way that this device will actually work. So how did this actually come about? Oh dear, I lost my place. Stand by.
He's forgetting where he is.
What it actually did was to use port numbers to actually do the translation between my device and the final destination. So what it basically comes down to is that every packet that goes out through this device gets rewritten as if it is the WAN address of this particular device. And so it's a clever technology that was introduced to extend the life of IPv4, right? The problem with IPv4 is that we have only 4 billion addresses total, right? And for every device in the world, there is simply not enough addresses. So what network address translation allows you to do is to pretend to be a different device.
I'm quickly approaching 128 used addresses at my house.
Right.
If you think about folks out there that are geeks like all of the guys that are on this call, they're going to have a lot of Ethernet devices too. There's a lot of geeks out there. There's a lot of people, and every device in the world now has an Ethernet port on it. TV sets, thermostats, you name it.
Toothbrush.
Yeah, it could be anything. You need to have IP addresses there for these devices. And if we were just using IPv4, we would be out of IP addresses, probably just with the folks that are on this call.
We've got a few questions. I know we've kind of talked about some of the private address space and some different things. This might be a good time to make sure that we've addressed them. It seems to be, you talked about the subnetting, and to a point, I don't know if you can see the questions or if you want me to read them.
It's hard to read from here.
The first one came in earlier, and I know, we said we talk about it from Travis. Does a subnet basically allow you to reuse an address, e.g. 192.168.1.100/24 for a device can be on the same subnet at 192.168.1.100/23 for any other devices?
Yes, so let me give a somewhat long answer to that. So let's say I am running the example that I've just described here, right? So I'm starting on my laptop and I have a to and a from address where the from address is what my laptop is really called. What happens is when I connect to this device, which actually does NAT, it basically goes and says, oh, yeah, well, I am not going to send it from 10.80, but I'm going to pretend that I am, what camera am I on?
You're actually on this camera, but let me get you on this one and Mark will switch to it.
I am actually going to pretend that that packet comes from 10.30.31.1, right? Because that is, oh, sorry, it's not 1, it's 199. That is actually what I am known to on this device. So then that packet makes its usual pass through to that device and it says, oh, okay, I know how to find 10.30.1.199 because I know how to get to the 10.30.31 network. And so when the reply comes back to this device, it says, okay, I need to send it to this. And it then says, okay, well, actually, I remember that I actually got this packet originally from this laptop. So it will rewrite the to address to then send it back to here. So the NAT table basically does the translation between the address that it's known to the rest of the network with versus the local address, which basically is how most ISPs work. So can you put up the, so this is what the network for most ISPs look like. So up here we have the internet. They may have a firewall or something like that, but then for the site, they would have a router that's, let's say, 10.0.0.1. There's a sector antenna that connects to all of the home sites.
This is wireless internet service providers. But where it says access point, it could be a cable modem concentrator. And each of these yellow lightning bolt links could be fiber or a cable of some kind.
True.
So this is pretty ubiquitous when it comes to the internet world.
And then within that sector, you have site 1, 2, 3, and 4, which has a unique address 10.003, 10.004, 10.05, 10.006.
All, quote, internal addresses.
Correct. But all of this shown with the lightning bolts is a subnet, right? It is the subnet of all of the devices within that sector.
Let's call it cable company or wireless internet service provider equipment.
Right.
It's their hardware. Comcast, it would be a Comcast address inside their network.
Correct. Then within each site, we have a local LAN. And the local LAN, in this case, is 192.168.0.1. And then there's another local LAN here, which is 192.168.0.1. and another one that's 192.168.0.1. Notice that we are reusing that subnet over multiple sites, right?
How can we do that?
And that is how we do that, because to the rest of the network, the address that it sees is 10.0.0.3 over here. So all of these devices here pretend or masquerade as 10.0.0.3 as a result of NAT, right? So what the NAT does is that translation between what its internal address and port is and the external address, which is universally routable, or at least, as far as the ISP is concerned, is routable, and then gets forwarded to the rest of the address. So this address, Google needs to understand. Google needs to know how to get to that particular address. But I just said that 10 dot is a private address. Well, sometimes there's something over here that's called carrier grade NAT, right? So
really, really fast, really, really big NAT.
right, if I'm using my iPhone, I typically get 172.16 or 172 subnet, right? That's because Verizon is not going to pay big bucks to give my iPhone a unique address. Instead, what they do is they give me a private address, and they do carrier grade NAT when I call outside the Verizon network.
So Travis, to answer your question, the addresses that you indicate there, the subnet inside your router would be a /24. So you could have 254 working devices in your network. You cannot reuse that IP address inside of your network, inside of that NAT. It cannot be reused. It can be reused outside of that NAT. But when it's behind your firewall, it's one for one. You cannot duplicate addresses. That makes a whole can of worms that you don't want to go to. A /23 subnet gives you two 255 IP address subnets. So essentially, instead of having 24-bit subnet mask and having 254 usable IPs, you have 512 total IPs
Right.
inside your network. So if you had so many devices that you ran out of IP addresses in the 255, you could make your subnet /23, and then inside of your NAT, you could have 512 devices. That's the difference between /23 and /24. It's what's happening on your local portion of the network, not what goes out to the cable modem, only what stays inside of your network.
Okay, good. Another question since we're on addressing here. I think it was from Ted. We covered part of it with the private address space, but he says, why not 9.30.20.6.7? And we talked about the 9 because we're using a 10 in its private space. But can you talk about the where we come up from an RMHAM perspective of the .30.20.6? In addition to the .10 network.
All right, so there was a simple address or a simple answer to that. There are essentially 3 sets of IP addresses that are allowed for private networks. 192.168 is private. 10.0.0.0/ whatever is private, and 172.16.0.0 is private. We used private address space inside of our network for various different things. The other addresses other than 10.172.16. and 192.168 are what's called a routable address. A routable address is an address that can go somewhere outside of your local area network and be able to find the other end without having to do network address translation or anything else. It's called a routable address. For example, if it started with a 9, it's going to be routed. You can't hear the question. Rich Painter couldn't hear. The question, can you back up so I can read that question? You'll have to scroll back on that screen. I can't do it from here. Why not 9.30.20.6? How was the 10 dot and 30 and 24 chosen for the RMHAM subnet? Sorry, I have to read it off the screen here at the same time. The reason that it was chosen was because we only use inside of our network private addresses. AE0EV Chuck just put in the private address spaces that we're currently using in the network. 10 dots are equipment in our network. 172.16 addresses are VPNs in our network, and 192.168s are home addresses in our network for QTH. If it's not one of those three, it's routable on the internet, and we don't have control over that. We're not using routable addresses on our network because we don't need to get to it from the outside world. And frankly, nothing on our network we want anybody except hams to be able to get to, and our equipment. We don't need that, what do we call that? DMZ traffic, demilitarized zone traffic, to get to any of our devices on the network. So it's all in private address space hiding behind firewalls. So if it's something other than one of those three prefixes that Chuck listed there, it's going to be routable, with a few minor exceptions that people will correct me about. But for the most part, what Willem has up on his presentation right there, showing those three, they are what are used outside of a firewall. So for example, the address that Willem listed, which was 23.237.17.75, that's the RMHAM network address. Notice it starts with 23. That 23 is world routable. You can get to that address from anywhere around the world, which brings up another huge problem: firewalls. What Willem's picture showed up here on that ISP diagram, make that full screen too. So if you take a look at this picture that he has right here, you'll see that orange block in the upper left-hand corner of that drawing. That firewall needs to be there if it's a world routable address, like a 23.237. It has to stop all the little kids sitting in China at their computers hacking on your devices. If you don't have that firewall, I can guarantee you that your computer is going to fall over and scream. But that's how we came up with it. We used what we could use inside. We could use 44 dot addresses, which are amateur radio network addresses. They're assigned for the Amper. It's called AmperNet. Is that correct? AMPR. It's very hard to use if you're trying to do world routing on those 44 dot addresses. Those would be world routable addresses, but because amateurs are cheap, it's very expensive to do peering to get connectivity to a 44 net. And you have to do some really funky things. So we chose not to implement 44 dot addresses in our network. Hopefully that helped. Did I go too deep?
No, that's
Okay.
good. So I'm going to take yet another strange deviation, which is I want to talk about ARP. So essentially what ARP does is it sets up the translation between an IP address and a MAC address, right? So I just showed you the ARP table that I have here on my laptop, and it's basically a name, which is, it actually resolved here the DNS name for that. And it says it's an Ethernet port, and then there's that hardware device, which is basically a MAC address. In order for any of this stuff to work, when I have one device talking to another device over an Ethernet link, at that lower level, they actually exchange information used on this, what's called a media access control address, which is a 48-bit address that describes a particular hardware card, right? Either an Ethernet port or a Wi-Fi port or something like that. And so what the ARP protocol does is start at the IP level and works its way down. So what it then does is figure out how these Ethernet devices will actually talk to each other. For the most part, we don't have to worry about ARP addresses because it just does its own thing and figures that out. However, with the MikroTik devices, that sometimes helps us tremendously. There is a protocol called MAC-Telnet and another feature that's called RMHAM, where we can actually talk between devices at the Ethernet level. And so if you by accident blow away the configuration on one of these devices, which I will not admit to ever having done, you can actually recover that device as long as you're either physically connected it by a wire or you can talk to it via RF. So as an aside, there are lots of asides in this talk, just because we're talking about 30 years worth of history that we sort of need to cover in order to explain how everything IP related works. So it's hard to tell a linear story. But so, as John indicated, the way that routing works in general is all you have to know is how to get the packet closer to its final destination. You don't need to know the whole path. All you need to know is what device to send that packet to next so that you can send that or move that device or that packet towards its next destination. And routing can be done in a number of ways. So if you're using NAT, you don't have to know anything, right? Because the network that you are becoming part of knows all the routing. So in the ISP image that we showed you, the ISP figures out routing for you. All you have to do is NAT between your network and the ISP's network, and everything just works. But in a network such as this, we need to do all of our routing ourselves. And there's a number of ways that you can do that. You can do static routing, which is we'll discuss next, or you can use one of the automatic routing protocols. OSPF is typically used for intra-domain routing, which basically means you own the whole domain and you're basically routing in it. BGP is for inter-domain routing. BGP is basically the backbone of the internet. It's basically how all of the various ISPs interchange. And there's a bunch of other protocols too, but those are the main ones that we need to talk about. Until 1993, we had something that was called classful interdomain routing. So depending on what your IP address was, you had a specific class of domains. So if you had a class A address, which started with something between 1 dot and 126 dot, you basically got a network with 16 million hosts. But there were only 126 of those, which back in 1980 was just fine, but today doesn't work, right? We had class B hosts, which was basically where the first two octets were 128.0 through 192.255. That gave us 16,000 individual subnets, each consisting of 65,000 hosts, right? So most universities got one of those class B addresses, right? So they were pretty big facilities where you could have all of those. And then there was a few class C addresses. Basically, those started with 192.0.0 through 223.5, 255.255. There was like 2 million of those, right? They were giving those out like candy back in the 80s. And each of those were 256 addresses that you could use. The problem is that were great in the 80s, but with the proliferation of internet access, there just wasn't enough addresses for everybody to use. So we came up with something called classless interdomain routing. So instead of always breaking the subnets on an octet. So either the first octet or the first two or the first three, the routing hardware was made smarter so that it could use a net mask of any length, right? So instead of just being 8, 16, or 24, you could make one that was 23 or 27 or 29 bits, right? And that was called CIDR, or classless interdomain routing. And so we still tend to follow the even octets. So like, for example, the /24 is what we use for the RMHAM network, just because it makes life easier. And we have lots of address space to work with. But unless you actually need 256 unique addresses at a site, you are not going to be using a /24. So for example, if you go to your ISP, you're lucky if they give you one unique address. And of course, you pay a bunch of money for it. But what they may give you is like a 29 address, right? Which is
/29 is 8 addresses, but you can only use 6 of them.
correct. Only 6 of them are usable because of the network and the broadcast address. But you know, a /26 address is probably going to cost you $50 a month right now.
Right now, I am paying per /29 about $15 a month for my data center.
Right.
And I have enough of them to do all of the servers that I have. I'm probably paying $75 a month in IP space alone. And they are really stingy about it. You have to prove to them that you need it.
Right. And so the whole idea is that they will give you an address, but that address will probably be either NATed, or if at least if it's not NATed, it's going to be one that they're going to just dole out as needed to you, and you get to use it for as long as you're up, and then it goes away. So the whole idea behind classless routing, where you can use not just /24, but if you need 512 addresses, you can use a /23, or if you only need 8, you can use /29, basically made many more subnets available for people to use. And even in that space, we are fast exhausting the IPv4 address space unless you resort to netting and using a private space the way we've done here.
And it's okay for us, most of everything we do. We're not an ISP. RMHAM is not an ISP.
Right.
Our intended use is to carry traffic from radio sites from point A to point B. We don't ever go to the internet intentionally.
Right, but specifically the 10 dot space that we chose is because it allows us to have 65,000 individual sites without running out of address space, right? And so we actually organize our IP addresses because we can be, we don't have to be frugal with our IP addresses into specific blocks. So for example, most of our sites is a 10.30 site. All of
That's
our links
Denver
are at
sites.
10.20, true.
Denver sites.
So we can make the addresses such that they actually have meaning to us beyond just being a number. And John already talked about this slide here, but there are special subnets. So for example, 0.0.0.0 can basically mean either any IP address, or if you add a /0, it can mean the default network. So, or the default, any subnet. So we use that in routing a lot. And then there are a few other special ones that I don't have time to talk about. I already mentioned port. So just one other thing to mention is port numbers are limited to 64K addresses. So basically 0 to 65,000. It basically means what program you want to talk to. So typically we write the address as an IP address and a dotted notation, then a colon, and then a port number. And that way you can address a particular port on a device. So if you want to talk to the HTTP address, you would add /80 because that's the well-known address for HTTP. If you want to send an email, you would connect to port 25. You want to do SSH, you do 22. But you also have an ephemeral port on your computer to say, this is the particular SSH section that I am talking from. So the operating system will randomly give you a port number somewhere between 1024 and 65,000 when you start a TCP connection, so that when this device replies, not only does it know what computer it needs to go to, but what specific terminal program I'm running, so that it will reply to the right device. So I was going to do NAT there, but I already did that. So let's talk a little bit about static routing, because that's where things get really interesting. What static routing essentially allows you to do is to send addresses that matches a certain pattern to a specific port. So the example here being Saddleback, right? Saddleback had 3 places it could send packets. How did it know which ones to send it to? Well, what you can do is go into that router and add a static address that says, if the address matches this particular pattern, send it to that particular port, right? Now, this is a pretty complicated thing to do if you have as complex a network as this. And we actually used to do things that way, but it required that every time that a link failed, you had to go and do a lot of manual reconfiguration of the network to keep everything going.
I didn't enjoy that.
I actually enjoyed that. That was pretty.
Jeff Carrier and I had a lot of sleepless nights.
The key thing, though, is that static routing still has a place in special cases. So, for example, if you have only one connection to the internet, or perhaps 2 connections, you can actually use static routing to steer the traffic in a way that you want. So how does it know where to go? Well, route matching is a very important item. So if you have a sequence of IP addresses or routes here that I've specified, so 0.0.0.0/0 is the loosest, it will go anywhere. 10.0.0.8 is less loose than the default, which is 0.0.0, but it basically limits it to just the 10 space. Then 10.30.0.0.16 is tighter yet, and 10.30.20.0/24 is the tightest route. So if I had routes set up for each of those, and a packet arrives to 10.30.20.6, the way that routing is set up is that it finds the tightest match. So in this case, because this is a /24 address, the first 3 octets match in this case, and it would basically say wherever that is routed to is where it will go. This address would also match, but because this one matches tighter, this is the one that gets selected. And the important thing is that when you set up routes, you don't have to deal with every last case. What you can do is you can say, in general, 10 dots do this. So 10.0.0.8 do this. But for 10.30.20.0, I want to do something else. And the 10.30.20.0 will override the default behavior and will do that again. That makes things practical. If I also had a route to, let's say, 10.30.10.0, because this one misses the 3rd octet, this route will then be ignored. And similarly, this one, because it's a 29, that's outside that range, that would also be ignored. So what I'm going to do to demonstrate static routing is to actually set up a virtual network. And that's, again, just a little bit of a sidebar, where what I'm actually going to do is I'm going to go from this demo device all the way, come on, to Thoradin using this white cable, except that this white cable is not going to be an actual real cable. It's going to be a virtual cable, right? And that's what a VPN basically is. It is a virtual connection where all my IP packets are going to be encapsulated in this tunnel to actually make the connection from one location to another. And so to make this a little bit more interesting, I'm going to remove my demo device from the internal part of the network and instead plug into the commercial internet here so that I can no longer reach the rest of my network. And instead, what I'm going to do is to set up a tunnel to basically go virtually through to Thoroden and then become part of the network. And this is basically a way that you can connect your mobile device or something else directly to a network without being physically able to actually connect to it. And it's also very commonly used to defeat censorship. So, you know, a lot of people in China, because they have the Great Firewall of China that won't let you connect to certain websites, people set up these VPNs to sites outside China, and then they can connect to wherever they need to. So basically what I need to do is I now need to reconfigure my device so that I can actually reach that. And I'm going to do that by setting up a tunnel to Thoroden. So the first thing I need to go and do is to connect my laptop directly to Mount Thoroden so that I can configure a VPN connection on Thoroden. So what I'm going to do there is connect to Thoroden and say, on PPP, I'm going to now add a new secret for a device called demo. Its password will be p@55wrd. Don't ever use that. That's a horrible password. Its local address is going to be 172.16.20.1, and its remote address is going to be 172.16.20.40. And when I now connect, it will set up a virtual connection over that particular tunnel. So going back to my demo device, I will now create a new SSTP tunnel. Whoops, sorry, I forgot to do that. That I'm going to call, whoops, that's PPP. Why did I end up in PPP? That I'm going to connect to Thoroden, which is
8.38.114.
And I'm going to be demo, and my password is going to be p@55wrd.
114, not 14.
Thank you.
Just one note on VPNs, we're not using PPTP anymore out there. It's been hacked and the Chinese kids are going crazy on PPTP. So if you're using PPTP anywhere, don't. It's bad. The amount of attacks that we're seeing come into these routers on PPTP is hundreds an hour. So we went through our network and turned them all off to something that was encrypted.
So in order to now make this work, I need to set up the connection to my network here by saying, okay, I've now got an interface called SSTP Thoradin. It has an address of 172.16.20.4. 40, thank you. But how do I now talk to the rest of this network? What I need to go and do is to add static routes. So if I say IP routes, you'll see that these are the routes that currently exist. 0000 goes to 192.168.1.1. That's my generic internet address. So everything is going to get sent there unless it is on the 10.30.80 network, which is my local network, or it's 172.16.20.1, which is the Thoradin address, or it is on the WAN, which is basically the 192.168.1.0 route.
Anything that's in that list, your router knows how to get to if it matches that.
And it tells you here how it reaches it, right? So it can go via Ether1 WAN or the bridge or SSTP Thoradin or Ether1 WAN. So to now add a route to all of the 10 dot addresses, so 10.0.0.8, I want all of that traffic to go where?
Somebody on the net?
I have to be able to reach that gateway already.
It's always the first hop.
So I want all of that traffic to be sent to Thoradin. Thoradin is 10.30.20. However, the port that I am talking to on Thoradin is 172.16.21. And check that gateway by pinging it.
What does that do?
Voila. Notice that it says AS, that's a static route that I have added,
It's, yeah,
sends all traffic to 172.16.20.1.
the A is active. If
Correct.
it's not active, that line is going to be blue and it will not have an A in front of it.
So if I now say, okay, can you ping 10.30.20.1, it works.
Magic.
If I now ping 10.20.10.1, it works. So any device on this network, I can now address. So again, great news, because now from my laptop, I can ping 10.30. Damn. Why isn't that working? Why can I not, from my laptop, ping 10.30.21, but I can from the router? Well, again, let's think about this. The router talks to, via the VPN, to Thoradin. When it sends a packet to Thoradin addressed to 10.30.20.1, what does it tell Thoradin the return address is? This router is 10.30.81, right? Does it use 10.30.81 as the source address?
That's not what you're connected to the other router on.
No.
You're connected to the other router on a 172.16.20 address.
Right. If I look at my addresses, notice that my address on the link to Thoradin is 172.16.20.40. When it sends a packet on that link, it sends it as the source address being 172.16.20.40. When my laptop sends something to Thoradin, it sends it to 10.30.20.10 with a source address of my laptop source address, right? Which is 10.30.82.50. The network doesn't know anything about 10.30.82.50. So what do I need to do in order for the network to find me? I need to go to Thoradin and tell Thoradin the way that you reach 10.30.80 is by sending packets to 172.16.20.40. Except I'm screwed because I am sitting at a remote site. I mean, even though I can touch Thoradin, I pretend that I can't reach Thoradin. How would I go and add a route on Thoradin if I can't reach Thoradin? Well, it's actually pretty easy because I can reach Thoradin from here. So what I can do is do 2 hops. So what I will do first is to say, connect to my local router. So now I'm logged into lab demo, which is what I'm here. And then from lab demo, I can log into Thoradin. And by the way, that's one of the really cool things about the command line on these MikroTiks. Notice that as I'm typing, the colors change. So the blue color tells me I've typed something valid. So if I type SSH, then I know now I've typed something valid. And I want to go to 10.30.20.1. And I've got things set up here so that I don't need passwords to log in. On the real system, don't ever do this. So now on Thoradin, what I need to do is to add a route. And notice again how it changes colors. So the destination address is what? It's 10.30.80. What am I going to put in for my address? I want the whole network, right? So the whole network is 0/2/24. That's my whole network. And what's the gateway? The gateway is 172.16.20.40. That is the address of the VPN on this router. And then I can, if I want it, I can add check equals ping just out of curiosity. Now, if I do IP route, notice that Thoradin has all kinds of routes in there, right? Because it knows how to get to all of these devices. But somewhere in this list, notice that it says, yeah, there's a static route that goes to 10.30.80.0 to using, oh, I typed that wrong. That's why it's not active. I need to remove Route 56. Oops, I just make sure that's right. Right. Yes, it's Route 66. So now notice that 10.30.80 is now an active static route that is being routed back to my VPN. And so now if I back out of here and I'm on my laptop again, now I can talk to Thornton, right? So here, this is the critical part of routing. What we need to do is to explain to each of these devices how you get to all of the subnets. By adding this VPN, what I have done is to basically create a way of steering all of the traffic for the RMHAM network to that particular address, but that's not enough. I need to also have the data from the RMHAM network come back to me, right? So in a static setup, you typically have to set a route on both ends. Otherwise, the traffic doesn't need to know how to come back to where you are. So I actually have something else here that talks about some other stuff, but I'm going to skip that because we're seriously running out of time. So the next thing I want to do is to set up something that's actually a physical route between two devices. So the first thing I need to do is go back to Thornton and remove the route that I've just had, because otherwise I'm going to have a conflict. Excuse me. So notice that now I can just directly go to Thornton. And I can take this static route out because I'm no longer going to need it. What I'm now going to do is to connect, instead of connecting to the commercial internet, I'm going to connect directly to SQA. And so now this orange wire represents a direct connection between this device and the SQA router. And so there's only one connection, which is a direct Ethernet connection as opposed to a VPN connection. And this connection is going to be statically routed. So this is how we set up all of these other static routes between devices. So in order to do this, I need to now find a unique address for this particular static route. And the way I'm going to do that is to choose it from the RMHAM section of static routes. So this is the configuration that we typically use for devices. We have address on SQA, which is 10.30.30. We've got a local address here of 10.30.80. And then for the link, we choose a new subnet address. So a point-to-point link is basically a special case of subnet, right? Where the devices on that link can talk to each other, and they basically share a subnet. So I'm going to make the SQA router 10.20.40.1, and I'm going to make my demo router 10.20.40.2. So just make sure I'm plugged into the right place. What I'm going to do is disable the VPN connection. I'm going to take that out. I'm going to remove this, and I'm going to set a new static address, by no longer just doing the, sorry, I'm messing this up. IP. You want to tell them what it is?
We have a motto for the RMHAM University, or for RMHAM itself, and it's DFIU, which yeah, F is a bird. Don't F it up.
So the address I'm going to set here on this WAN is 10.20.40.2. And I'm going to put /24 on that. Basically, by doing that, I am defining the subnet as 10.20.40, and I am going to be .2. The convention that we follow is that the .1 side is the side that is closest to Thoradin, and the .2 side is the other side. So I've added that particular route. And if you actually look at my IP routes, it says, oh, I know how to reach that because it's directly attached network. What do I now need to do at Thoradin to actually, at SQUA to make this work? Well, I need to also give it an address. And let's see if I can reach you directly. Come on. My screen isn't big enough to actually allow another Winbox. Going to have to plug directly into SQUA. Whoops, all right. Plug this into the wrong hole anyway. I'm going to become part of the SQUA network. And on SQUA, I am going, whoops, go away. Going to add a new address. Now, notice that I'm putting this on port 3. That's what makes these microtics so powerful, right? I can do this on any port that I want. I'm going to make this address 10.20.40.1/24. Now, if I try to connect to the adjacent device, notice that these two guys are now talking to each other over this orange wire. However, what's the other thing that I'm going to need to do in order to direct traffic from SQUA to this device? I'm going to have to add a static route, right? So on SQUA, I need to say IP route, add a new static route to 10.30.20, sorry, 80.0/24. But what's the gateway now? .20.40.2. How do I know that? Because the 10.20.40.2 address is the address of this IP port. Can I already reach it? Yes, I can, because it's a directly attached network. So as long as I add that, I can now say tools ping 10.30.80.1, and I can reach the demo network that way, right? So notice what I've done is exactly the same thing that I did before, except that instead of connecting it via the VPN, I have just connected it via this orange cable directly. And so now if I plugged into the local network again and try to route from there, you'll notice that my laptop can now basically ping 10.30.20.1. And if, whoops, well, I clearly messed something up. Did I plug into the right network? Why isn't this working? That's the great thing about demonstrations. If things don't work, you can pretend like it was supposed to, right?
It's not like this has ever happened before.
I set a route from that side to me. I didn't set the route the other way, right?
You have to have routes going both ways.
I
If you
have
don't have
to
routes going both ways, it will break.
Right, so, whoops, sorry, I didn't want to bring up my mail. If I can click straight. I need to also, on the local router, set the outgoing route. So what traffic am I going to route going out? It knows how to get to 102040, 103080. It doesn't know how to get anywhere else. Should I add send 10.0.0.0.8 that way? Well, I could, but there is no other way out of this router, right? I might as well make that the default route. So the default route goes to where? What's my gateway address?
The next hop.
The next hop, which is 10.30.31.1, right?
Your link address.
No, right? 10.30.30.1 is what this router calls itself internally. On this orange wire, it doesn't call itself that. It calls itself 10.20.40.1, right? So you have to get the address on that local link, which is 10.20.40.1. And I typically add ping just to make sure that it actually works. Notice that that first came up blue and then turned black. Blue means it was a route, but it wasn't active yet. So till it sent those first few pings and made sure that everything worked, that route wasn't working. And so now it's going to work, right? Of
We'll see.
course.
The proof is in seeing. I'm from Missouri. Show me.
So I can actually run cping here. Actually, let me do it this way.
cping is a really nice tool. If you guys do any IP stuff yourself, I would highly recommend getting a copy of this, and it's available on Willem's website, and he can send a link to that.
And it actually works on OS X and Windows now as well. So thank you for the
It
people who
has
helped
some
me with
weird idiosyncrasies with Windows. When you resize
that.
the
Windows
box.
is just a piece of
Did you say that?
Forgot I was at a live mic. But so basically I can see everything. So that's everything, of course, is working now. So the last thing that I wanted to show you today here, and then we'll call it quits, is right now I am connected by this orange wire from here to there. But in reality, I'm going to need an RF link to go from here to there, right? So how do we set up those RF links? Well, that is why I brought these two guys.
You tell Mark to go up on the tower and freeze his butt off is what you do.
So I'm going to set up an RF link.
You promise
And
this is going to work?
it worked yesterday. And what
this is live. You do know that, right?
yes.
You know what happens when you do this live? It doesn't
Um,
seem to work.
So I'm going to power this up and plug the lovely pink wire in where the orange wire used
What's
to
the
go.
little thing that you got there in your hand?
This is just a power injector.
What's
So
that do?
it basically adds 24 volts and then runs power up the Ethernet cable so that it powers the device at the same time. I'm going to plug this into here.
How come you don't use the yellow port on there?
Well, I don't, this is only 12 volts, and I don't know that it has enough power to actually run this radio. And so
One note here, those routers will run from 8 to 36 volts. And these radio devices really, really like to see 24 volts. And because this whole board is running on a 12-volt power supply, we're using an external 24-volt supply to power this thing just to make sure that it has enough current to drive this.
And so this device is now going to slave to this one. And I'm going to take the purple cable that comes out of it and replace the orange wire with that. So basically, I've turned this wire into the purple wire that runs to this device. This device connects via RF to microwave to this device. And then the pink wire runs back into SQA. So now,
So essentially what you built is nothing different than what you had, correct? You
that's
have that
correct.
wire,
Instead of having a wire, I now just have an RF bridge.
but it's really no different. It's still the same thing. It's whatever goes in comes out. It looks like a wire to the devices.
Assuming I didn't screw it up, yes. So here's the proof of the pudding. Voila. I can still, from my laptop, which is connected via the blue wire to this device, then via the purple wire.
How do
to-
you prove that it's actually going that way?
Let's pick Thoradin. So it does 103081, which is my gateway. It goes to 102041, which is SQA. Why isn't there anything in between? What about these guys?
They look like a wire. They're transparent.
Right, they are a bridge, right? So remember what we talked about, the bridge? It just sends everything that comes in the wire over the RF, and everything that comes back in over the RF goes back over the wire. That's a bridge. You don't want to do it system-wide, but on a link,
A single link,
that's what
two
you want.
devices.
Two devices, it's a point-to-point link. So since I still have a few minutes, let me, whoops, sorry, that's the wrong button. Let me show you how I can actually talk to that device. Our convention,
Mark made a comment there. He said, do a trace route and see where it breaks. That's what you did with CPing.
right,
And let's see, Jeff said, yes, please, would like to use CPing. And Chris Keller sent Willem's website with the address to get it.
okay, yeah, Chris, add cping.zip to it. That's the, because there's a bunch of other crap on there. So I happen to know that those devices, if I can type,
Thanks, Chris. Chris is one of our NetOps guys, so he's lurking in the background.
so here I am actually now connected to 102042, which is called demo to SQA, which is this device over here. So, oops, sorry, zoom in, not zoom out. So if I go to IP addresses, this device has a single address that is on its bridge. If I actually look at the bridge, it has only two ports. It's the Ether port and the WAN port. So everything here that comes in is going to go out. Now it's a little smarter than just sending everything because it knows what's on the RF side versus what's on the
And
Ethernet
how does it
side.
know? ARP,
Right, the ARP table tells it which way it goes, right?
Address Resolution Protocol. The radios know everything that is on that device because it's listening all the time to see what devices it hears.
Right, so 1 and 2 is the far side and the near side. It knows what's there, right? But again, to just put in a little plug more for the MikroTik devices.
I've been using MikroTik devices since early 1990s.
The
And
nice thing,
I'm telling you that they have come a long way since then.
well, sure, that
They
is
are
sure.
phenomenal. They used to be a simple garbage in, garbage out packet router. Now they do everything that multiple $1,000 Cisco's do for 10 cents on the dollar.
What else is particularly nice about these 5 gigahertz radios is notice that I picked a frequency that is in the ham band, 5900
It's
megahertz.
5650 to 5925. That's the ham band. But the bottom several hundred megahertz is in the commercial band too.
Right.
We share the 5 gig band with all of the wireless ISPs on the planet. So the top 80 megahertz of the band is what we end up using because it's quiet
Correct.
for a while.
For now.
They just gave away our 3 gig spectrum, so we
Yeah,
lost
that
that to
that-
commercial entities.
That's why that guy's lying there.
But the 5 gig will likely go that way soon. They did give away specific licenses recently to internet service providers that wanted spectrum for COVID. And here in Colorado, there's a few places down around Colorado Springs and one in Douglas County that petitioned the FCC to be allowed to use those frequencies temporarily. Kind of a bummer.
So the critical thing in order to make this work is, number one, when you buy the hardware, you have to buy the international version. If you buy the US version, you can only use it commercially.
You will have some issues with some vendors purchasing international versions to be shipped inside the United States. We have found a couple of vendors that will allow us to do that. BalticNetworks.com out of Illinois is one of those vendors that will allow you to purchase it with an amateur license. There's another one called Streakwave. I believe that they're out of Florida. They will allow you to purchase it, but every time you purchase something, you have to fill out their form and send a copy of your license. Baltic is our choice, and their shipping is slightly higher, but they're a lot easier to work with.
And I think ISP Supply is another one.
Yes, out of Texas.
And I filled out, they send you a form to fill out, and once you filled it out, they open up the catalog so you can order the international version.
Okay. So the key thing that you need to do here is you have an advanced mode and a simple mode. So this is advanced mode. Once if you're in simple mode, you're tied to a particular county, a country set. If you're in advanced mode, you can change the frequency mode here to super channel. And once you change it to super channel,
You can go anywhere.
you can pretty much go everywhere. You can also go outside the ham band into places where you need not to be going.
Okay,
so-
be aware. There's military stuff there. There's commercial stuff there. And if you're stomping on those guys, you're going to have guys showing up knocking on your door asking why you're doing this. So you need to know that you're putting this radio in the right place. These radios run 20 megahertz wide channels. So the center is where you're putting the radio. So if it says 5900, the bottom is 5890. The top is 5910. So you're actually using 20 megahertz wide based on the center channel that you set. So if you were to go to 5925 and you set this radio to be 20 megahertz wide, you're 10 megahertz into places you shouldn't be. Be very, very, very careful where you set these radios. You need to know what you did.
Sorry, I didn't quite catch that.
Thanks, Siri.
Siri clearly is not paying attention to this class. In my case, because I am here, the client, I set the frequency up here, and I also have to set the scan frequency down here. If I set it to scan list, it'll basically hunt everywhere. If you set,
If you set it to default, it will only scan commercial channels too, and you'll never be able to get the link to come
oh,
up.
that's good to know. So both of those needs to be the same setting, and it comes up very fast. The other thing to do here is to set the wireless protocol. So the Wi-Fi protocol that we generally use is called 802.11. It works well for short distances, but for these really long shots, you really want to set this to what's called N-Stream. N-Stream is a MikroTik proprietary variant on 802.11.
But it's still legal to run in the ham band.
It's still
Perfectly
legal to run, but it it deals with the fact that the time to send a packet and get an acknowledgement is now getting into the microseconds.
Things get really flaky past about 35 miles on these radios. And if you're running 802.11, all of a sudden your packets are going to start failing, and it's going to be like your link is down, but it's really not. It has to do with the time window that the radios wait for the packets to come back in. If you use Endstream, you can go 150 miles. It doesn't care. If you've got enough signal to go that far, it'll happily do it.
So basically, by setting this on both sides, if I can go to my registration list here, you can see that I connected to the other device. Oh, I forgot to point out one thing. In order to be legal in the ham band, put your call sign in as the SSID. That way, you're legally identifying.
Glenn has a question here. Is the MikroTik device the hex PoE Lite? These devices are a bunch of different devices. Hex PoE Lite is one of them. We like to use one of two devices for this board here. We're using RB750s and we're using RB951s. These plastic case devices do leak a lot of RF, and it will tear up VHF badly. Just be aware of that.
Well, and also if your shack is directly under your antenna, get 2011 because it has a metal case.
They also make a small desktop version of that,
And
which is very nice. And the metal case will contain, yeah, this one that's up here on the board here.
That's also a 2011.
Let's turn this up here. Maybe. Got to move the camera. All right. I'll switch in the other camera so we have a little higher resolution here.
That's the desktop 2011.
This is the desktop 2011, and it has Wi-Fi in it. These are, I think, about $130. It's 10 ports, plus it has an SFP port. If you look right here at this location, that's a fiber slot for an SFP, which allows you to interconnect to switches. And this is an SFP only. It's not SFP plus. It will not run 10 gig. This device will only run 1 gig. But that device, it has a metal case and it contains the noise. And these
will also keep the noise prevent the noise from coming in.
It will keep the noise from getting in, like RF from high power broadcast, which some of us have. These devices, they tend to radiate on these cables because these are not shielded cables. That shielded cable is a very important thing. When you install these things in an outside environment, putting them on a piece of cable that has a grounded shield is extremely important. There goes the Jet Ranger.
So I have one last thing to demonstrate, which is I am on the far end of RF link where the gateway is on the far end. So I am going to try to ping 10.20.40.4. Now that device I am directly connected to, right? However, think about how routing works. I am on 10.30.80. How do I reach 10.20.40.2? I'm going to this device and saying, I need to talk to the device on the other side. What if this device just lost power? I'm still directly connected, aren't I? Crap. Never mind.
Should have gone the other way.
Yeah. If that device loses power, I can no longer talk to that device because I need to go through the .1 gateway.
So if you're on the far side, on the .2 side, and you're trying to get to .2, and the .1 is down, how do you deal with that?
So what if I am trying to reach this device from somewhere else than just 10.20.40.1? Can I add a second default route that would go the other way? So notice that I now have two routes that are the same, except that this one goes to 10.20.40.1, and this goes to 10.20.40.2. What would happen if I turn this on? Well, if I set the routing distance to 2, notice that that blues out, right? And it blues out because there is a route with equally tight matching that goes to 10.40.1. But the distance is 1 instead of being 2. What if I fail the route on the other side? I've just powered down this device. It's no longer reachable. Did I unplug the right one? Yes. Did I? Oh, I know what I did wrong. Sorry. Pretend that didn't just happen. Come on, why don't you fail? There we go. Notice what just happened is the route that used to be black went to blue, and the route that used to be blue went to black. That is what we call failover, right? So I have set a distance of 1 to my desired default gateway. I've set a weight of 2 to my backup default gateway. And when the default gateway went away because I powered it down, it basically said, I can no longer reach that device. I will now go to this other static gateway, which it happens to be able to reach, right? So that's an example of route failover, where you've set the distance as the preferred sequence in which you want things to fail. And then as that one fails, it goes to the next one. And what I had forgotten to do was to say, ping the other device to make sure that it's still alive, because it's on the other side of an RF link. The RF link on this side is still up. It's just not passing any traffic because the device on the other side went down and forgot to set ping. So that's why it failed. Okay. So what I was going to show you is how to also set up OSPF and BGP and all of those other kinds of things. But in the first place, it's 11:30. And I think most people's heads are full at this point. So we'll call this a day. And if you're really interested in how to do OSPF and all of those kinds of things, we typically have a NetOps training session here, like every couple of years or so. And where what it's all about in that particular case is how do you make OSPF work and do automatic routing as opposed to. So we're going to call it a day with that. Thanks again to John and Rob for providing all of the AV equipment. Hopefully, yes, Mark Skelton is our director of audiovisual production.
We know how to make the video not choppy now, so we'll have that fixed by next time.
Yes, and please come and join us next month, which is December the 12th, for Dean Mertz's presentation on measurement and test equipment. Do you want to come up here and say something about it, about what you're going to talk about? Come over here so they can see how you're talking. I'll appropriately social distance here.
Yeah, hi. We'll talk about some test and measurement techniques for hams, and also one of the things that I've been traveling for years and years in Asia and have seen lots and lots of really budget test equipment, some of which good, some of it look pretty cheap. So we'll try some of those out and see if you can actually use some of those, $50 oscilloscopes and things like that for ham use. So
I think his mic's off, not hearing anything.
I don't think your mic was on.
Yeah,
Hey, you're not social distancing this time.
technical issues there. Yeah, hi, I'm Dean, K0MKT. Come on down next month and we'll talk about test and measurement equipment, some techniques for hams. And, as I mentioned, we'll look at the budget equipment. There's a lot of really cheap analyzers, vector network analyzers and scopes and signal generators and things like that. And we'll see if they really do anything. And we'll even pop a few open because as Dave Jones on the EE blog says, don't turn it on, take it apart. And we'll do that too.
Okay,
So we'll stick around here if there are any other questions that people are just dying to get to know, but otherwise we're always available by email to answer questions. And if you have any feedback on ways to make CPing more interesting or better,
we'll also have this
we'll work on
presentation
that.
up locally within the next day on YouTube, and it won't be jumpy. So
Okay.
if you want to see what it really looked like, you can.
Okay. So Mark, did you have something?
So you may want to make, one comment about maybe shutting your Wi-Fi off on the computer if you're playing with test labs and some different things, or you're putting new equipment on the network to deploy.
Yeah. Well, not like I would have ever done this before, but one of the features of the NetLab is that the IP addresses on the NetLab are the same as the IP addresses on the mountaintop. And the rule in RMHAM NetOps is if you blow
DFIU.
away the configuration on a mountaintop radio, you better fix it before Observium alerts, or else your name's going to be
You
mud.
have a half hour now.
So it's 25 minutes before Observium sends out an alert to everybody that tells them that you've messed things up. So the way that we do it on the NetLab is the username is the same, but the password is different. So if it asks you for the password,
Better not type it
don't
in.
just type it in because you're in the wrong device. Also, all the devices have a lab in front of the name. So if you pay attention, you shouldn't do it. But I know of people who have done it before. Although...
Yeah, I think all of us in this room have done that. All right. Thank you
Okay.
very much.
Thank you, everybody.
Looking forward to see everybody next month.
Talk to you all later.
Thanks, guys.
I have a question. This is Rich. Anybody there?
Yeah, go ahead, Rich.
Oh, okay. I was hoping we'd get to the OSPF, which I was looking to get the meat of that. So let me ask a related question. On all the mountaintops, are they all manually created static routes as you manually walk through an example today? or is there some more global automated way that you configure these?
They're all running OSPF, so it's very minimal configuration. In this whole NetLab, there's probably 3 total static routes. Everything else is done with OSPF. I wanted to talk about OSPF today, but John said, remember, this is an introduction to IP networking. So OSPF is a little bit far advanced, so that's probably going to be a different class. But in the RMHAM network, the only time that we have a static route is if there's only one way in and out of that site, which is pretty rare. Most sites have multiple connections. And so basically our entire network is OSPF routed with the automatic failover that you get out of OSPF.
Well, I'd encourage us to have an OSPF class sooner than next year.
Well, we've inflicted that class on all of the NetOps guys. We can always do it as an RMHAM University, but our schedule already for this year is full. So we'll do OSPF on next year's RMHAM University schedule.
Well, do you have your any previous OSPF class recorded? I could just watch.
I don't think we recorded it, did we? No. Well, it wasn't so much a class as a workshop that we did last time, so we didn't record it.
We just started doing recordings this year, so
Right.
it wasn't something we had done in the past. When the world changed, we started doing it electronically.
Yes, and we're still learning. We'll get better as we go on. We have all of the gear now. We just need to learn how to use it.
Any other questions? Comments?
Somebody's going very digital.
Yeah, somebody's really digital there.
You sound like Mickey Mouse.
So Mark is trying to ask a question, N9 EDK. He was wondering if you can pass options, ping options in the config file for CPing.
That's one of the things that I was actually is on my schedule to work. There's a few things that I was going to add to CPing, but all of the options are on the command line at this time.
Yeah.
I wrote the TCP enhancement and sent it back to you, Willem. That you could use TCP instead of just ICMP pings.
Right. I'm actually working on a version that will allow you to do TCP and UDP and everything else under the sun. I just haven't gotten it to a state where I can release it yet.
Oh, okay. Well, if somebody wants my version of yours, I can provide that too, because I've tested it. It works pretty good.
Okay. Anybody else? That's a great one.
Let's see if we can see this. Here, let's try this camera. Maybe it'll focus on it.
Go to xkcd.com. It's today's XKCD. Oh, actually, yesterday.
It says welcome.
Is that today's or yesterday's?
Yes, yesterday.
Welcome to your final exam. The exam is now over. I'm afraid all of you failed. Your grades have been stored on our department server and will be submitted tomorrow. Class dismissed.
Yes. See if you can hack the department server. Yeah.
All right.
Looking for the ability to use different interfaces on the Linux host. Can you explain that a little bit?
I think he wants to be able to route the multiple interfaces. It's kind of tricky using.
Oh, in CPing. Okay. No, so on CPing, it basically uses the system default route to basically send it on the interface that.
But you could create static routes based on interfaces with Linux, depending on your Linux version. Your mileage may vary, Google it, and it will tell you how to do static routes for multiple interfaces. I do it all the time. And
Right.
It's not beginner stuff, but it's not rocket science. It's pretty easy.
Right, but I mean, but the reason why I didn't add that to CPing is that what I'm trying to do is just see what the operating system is doing, rather than, like for example, in ping, you can say ping out over this interface and see whether you get a reply. In CPing, basically, I said, I'm trying to test the operating system's ability to route this packet. But that's certainly something that I could do that on each of the configuration lines to say, not only what IP address to send it to, but over what interface to send it. So that's actually, it's not that hard to do. It's just that because of the way that the kernel associates the interface, I'm gonna see if I need to do open a separate port, or is it just the same port? But I'll look into that. Right. Okay. Yeah. That's a use case that I didn't foresee, but that's something that's something that I can add. But my first thing that I'm halfway done with is also being able to use TCP SYNFIN packets to basically just do a half open connection using TCP, so you can see whether a service is up as opposed to whether a device is up. So that's the thing that I'm working on next.
Anybody else
That's
have
all I got.
questions? All right.
Okay, thank you very
Failing
much.
that-
We appreciate you attending.
Thank you very much.
Yes, CPing is open source. On the website, it's both the source code and the executable. Basically, it's GPL. So if you make it better, send me a copy of your improvements.
So you can order more stuff. There's a place to stuff.